Good afternoon, everyone. Welcome to today's talk on Flink SQL and TableAPI. I'm Xiaowei, and this is my colleague Shaoxuan. First, I will give some background about Alibaba and our group, and then I will talk about why we choose SQL and TableAPI. Shaoxuan will talk about much more details into SQL and TableAPI and its usage at large-scale production. Alibaba operates the world's largest e-commerce platform. Singles Day, which is November 11th, is the largest shopping holiday in China. To give you some rough idea, in 2016, the United States of America recorded sales of about $3.4 billion on Black Friday. And on Cyber Monday, it recorded another $3.5 billion. So they add up to around $7 billion of sales. In comparison, on Singles Day, Alibaba's Taobao and Tmall platform recorded a GMV of $17.8 billion. So it's much larger than Black Friday and Cyber Monday combined. We are part of the real-time data infrastructure group. Our group is responsible for providing the real-time data processing infrastructure to our internal products, such as the Tmall, Taobao. In addition to that, we also support the external customers through our cloud offering. We started looking into Flink about 2 years ago when we realized that we need a powerful computer engine that can unify both batch and streaming. When we saw Flink, we were very impressed by it. In Flink, it treats batch as a special case of streaming. A batch is basically treated as a finite stream. So we decided to use Flink for our production, but we quickly realized there were a few limitations in Flink which could be problematic at large scale, such as Alibaba. So we started the Flink project to fix these problems and make Flink work well at a very large scale. Over the course, we have made various improvements in Flink's runtime. We also enhanced the Flink SQL and TableAPI greatly and made it production ready. Since last August, we started working with the Flink community to integrate our changes back to Flink. So far, we have already made several key improvements to Flink. We also made hundreds of patches to Flink. Here's a quick overview of the Flink ecosystem at Alibaba. On bottom of the stack, there is the cluster layer, which in the case of Hadoop, we have Yarn for resource management and HDFS for storage. On top of this, running on top of this cluster, we have the Flink computer engine, which includes a runtime part. On top of runtime, we have the data stream API for streaming and dataset API for batch processing. On top of these two API, we also have the SQL and Table API. On top of the Flink computer engine, we have the platform layer, which consists of multiple platforms. The most important ones are the machine learning platform and the stream computer platform, which makes it easy to write Flink jobs. With these platforms, we are able to support various products inside the company, such as search, recommendation, and advertisement. Now let me give you some background reasoning on why we choose SQL. As I mentioned a bit earlier, the main reason, one of the major reasons we choose Flink is Flink treats batch and streaming equally. They in a uniform way in its runtime. However, at the API level, Flink still offers two sets of API. It offers the dataset API for batch processing and data stream API for streaming. This is kind of unfortunate. So in the case that you have both batch processing pipeline and streaming pipeline, you will need to write your job twice, one for your batch pipeline and one for your streaming pipeline. it's not only more work, it also, sometimes it can also be tricky to make sure these two pipelines are consistent with each other. So in an ideal world, we would like a single API that have consistent semantics between batch and streaming. So a user only need to write their pipelines once and be able to run it in either batch or streaming mode. So we started to look into SQL. SQL is well known to be very good at describing your data processing logic. With SQL, users only need to express their semantics of their data processing and don't need to worry about the implementation details. They can also leave the hard optimization problems to the optimizer, to the system, and be assured that he can get reasonable performance out of it. In addition to SQL, we also look at the TableAPI. TableAPI, you can basically view it as a Scala version of SQL, which integrates very well with language such as Java or Scala. Another benefit of TableAPI is it makes very easy to extend standard SQL in case we need it. So in the case of batch processing, using SQL to express the data processing logic is pretty straightforward, and that is done in a lot of places. But in the case of streaming, we don't even have a table. How does SQL make sense? To solve this problem, we need to generalize the concept of a table to make it work in the case of streaming. In big data, we usually consider tables as something immutable, as something that's static. But in the case of streaming, there is one important difference is the contents of a table can actually change over time. So we introduce the concept of dynamic table. A dynamic table is basically a table which changes over time. The interesting thing is about dynamic table is that there is a string table duality. Suppose you have a string, you can treat each event in the string as a changelog to this dynamic table. We can define two operations. The first is the apply operation, and the second is the changelog operation. In the apply operation, we apply the changelog from the string to the dynamic table. So you get a table whose contents change over time. And on the other hand, if you have a dynamic table, you can derive its changelog as a string of events. So if you get a string, you apply its changelog to the dynamic table, and derive its changelog, you get another string. The interesting thing about this is these two strings are the same or equivalent. You can do this thing the other way around. If you have a dynamic table, you can derive its changelog first, then apply the changelog. You will get another dynamic table, which is equivalent to the dynamic table that you started with. So in some sense, the string and the dynamic table contains the same information. And this is the so-called string and table duality. With this duality, it's possible to consider string as a table, as a dynamic table, which is a generalization of static tables. Let's look at a bit more details on the apply and the changelog operations for between the string and table duality. When we apply the changelog into a dynamic table conceptually, there are two modes. In the first mode, the dynamic table does not have any primary key. So each event in the changelog string gets appended to the dynamic table. Hence, all the records in the string becomes a record in the corresponding dynamic table. This is the simplest one, the append mode. But in addition to append mode, we also have an update mode. In this mode, the major difference is the dynamic table conceptually has a primary key. So when we apply the changelog from the string to the dynamic table, sometimes it results in an insert. Sometimes it can also update the existing record, which becomes update. And in some other case, it may become a delete operation on the dynamic table. So with this apply operation, the dynamic table can express the dynamic table is connected to the string of changelogs. Let's look at the other way around. Suppose you have a dynamic table and you want to derive its changelog. In this case, you have some options. The first option is when do we emit the changelog? This is the when question. The simplest choice is every time when any record changes in the dynamic table, we generate a changelog in the string. But this is not necessary. You can also decide when a record in the dynamic table changes multiple times, we only generate a single changelog record in the string. So this choice of when to derive the changelog offers us some freedom. This freedom is actually important when we do optimizations. In addition to this when question, we also have some freedom in deciding what information we include in the changelog. The simplest mode is the redo mode. In this mode, we only record the new value of the updates in the changelog. So this changelog allows us to recover the dynamic table's contents. In the second mode, it's the redo plus undo mode. In this mode, the new value as well as the old value gets emitted in the string's changelog. This string allows us to reconstruct the dynamic table as well as undo it. That's why we get this name. So with these two operations and the duality between table and the duality between string and dynamic table, we basically unified the underlying data between batch and streaming. In both cases, they can be viewed, the underlying data can be viewed as dynamic table. Just in the case of batch, the dynamic table degenerates into static table, whose contents does not change over time. Now let's look at how SQL works in the case of streaming. In the case of string program, usually what you get is you have a set of input strings and you have a desired output string, and you want to express your processing logic to go from these input strings to the output string. So the first thing you do is for each string, you conceptually convert these strings into dynamic tables using the string and table duality. What I want to point out is you do this conversion conceptually in your mind, you don't do it physically by materializing the data. Once you do this conversion in your mind conceptually, basically you convert the problem into you have a set of input dynamic tables and you have a desired output dynamic table. You need to express your data processing logic on these dynamic tables to produce the output dynamic table. So you can write a SQL statement, just like in the batch case, to express your data processing logic. If your SQL statement works at any time, basically this becomes a continuous query. And this continuous query expresses your string processing logic. To summarize, the dynamic table generalizes the concept of a static table in the batch case. And once we have the dynamic table, we can use the same SQL to unify the data processing logic in both batch and the streaming. The important thing is the same SQL works for both batch and streaming, and there is no need for string SQL. Now I hand off to my colleague Shaoxuan. He will talk more about Flink SQL and TableAPI.
Okay, thanks, Xiaowei. Hello everyone, good afternoon, thanks for coming. My name is Xiaoxuan. I'd like to continue our talk on Flink SQL Table APIs. I hope you get the point of dynamic table here, and also as Xiaowei mentioned, Table API is just a Scala Java SQL. So in the following presentation, when I say SQL, means infers both SQL and the Table API. I have two sections. One section is Flink SQL and Table API. The other section is about the large production at Alibaba, how we're using SQL in large production. So this is the agenda for Flink SQL and Table API. I will start with a simple query and how it looks like in the streaming, select and where. And then I will talk about streaming, inner join, how it looks like in the Flink and how it's implemented. After this, I will introduce three user-defined functions, UDF, UDTF, UDAGG. And those three functions is very helpful. It's allowed user to describe their business logic, but they are different in terms of like major difference is the input and output. For example, the UDF is inputted Scala and generate Scala. UDTF is one Scala input, generate a table, while the UDAGG is inputted table and you aggregate everything and you have one Scala result. So those three functions covers three scenarios. After this, I will talk about the retraction. Retraction is really, really important for the streaming. The batch query, batch SQL doesn't have this concept. It's a building block component from our point of view for the dynamic table. If you remember the undo processing, basically you have redo and undo. Retraction is a motivation for the undo. And finally, I will introduce the aggregate. It's including the grouping aggregate as well as the over aggregate. Okay, let's start. Look at the simple query. Select and where. This is quite similar as a batch query. So imagine you have a table. So I think Xiaowei mentioned there's duality between streaming and the table, right? So here, if showing table, but actually it could be the streaming. You have Kafka logging, and you have each line as an input, and you separate the lines to the table for each rows, then you get the table. So here table, you can imagine it also can be a stream. So when the streaming come in, you have a table looks like this, and you have here the example, you have multiple columns. You can select whatever columns you want. In this example, I select all the columns, 5 columns. And also, if you are interested in a certain pattern of the data, for instance, in this case, I only want to have the result where the name is equal to Latte, right? So you're just using where clause and basically apply the filter there. Then you will get, this is your input, and this is the bottom is your output. So select where it's very useful for user to select the data, whatever they want. But this is your luck. It's lucky, right? So all the data is in one source, one table. What about imagine in streaming, there are some columns in another source. There are others in another source. There are basically 2 sources have different columns you are interested. So this problem basically, for example, previous cases here, the name stock in one left table and the price sales in another table. If you want to get a similar result as previous query, you basically need to connect the tables. So this is called a stream join. And in this case, if the key matching, it will generate result. And the highlight part in the yellow is 3 water. This is only showing on the left side, not on the right side. So some users don't want the intermediate result because it's just a partial result. It don't want to emit it out. So this query is called inner join, right? So only data is showing with certain key, only showing on the both left side and the right side. It will emit out. So this is together called the stream inner join. And how is it implemented in the Flink in the operator level? So one simple approach is that you have to, anyway, to buffer all the data for the streaming join, right? So you cannot losing any data previous happened. So you have to buffer everything. One simple approach is that you can buffer the data in the memory, but you have very quickly get auto memory problem. The other thing is for streaming, we have to handle failover. If you buffer data in the memory, and if the machine is down or the job will crash, you lose the data. So to get reliable streaming working and exactly one semantics, you have put all the buffer data into the state. So then the idea is that connect two stream and create two state of table, and the left table and the right table. Whenever each side has a result, incoming data, you will check the peer side. If it's existing, you send the result and save to your state. Otherwise, it just save to the state. So to handle state is actually very complex in the streaming system before Flink. Flink is really, really powerful. At the first beginning, at the first day, it's look at the state problem, design a very beautiful interface and efficient interface for the stream operations. So this is the inner draw. Let's look at the other UDF functions. So as I mentioned, UDF is converts multiple scalars in one line as an input into a scalar output. So in Blink, the UDF is very easy to create by user. User just need to, define their business logic in one single evil method. And this method can be overloaded with different parameters, input and output. And moreover, we recently add support for UDF and UDTF together to support different types and dynamic inputs. And in this case, is example showing that when you create a UDF like this, and the query basically takes the first two long type value and add together, generate one result as a sum. And another query is take three input and generate one result. So basically, here you take the multiple scalars and you generate two scalar because you have two UDF. It's simple, right? A UDTF is that you have one scalar input and you generate a table. In this case, you have line of string and you want to separate this line by space into different rows. And the column is separated by the shell. So similar as a UDTF users still just need to implement their processing logic in the evil, and in addition, you just need to create a collect, using the collect method to implement how the table looks like, the logic basically designed by the collect method. Okay, the third one is the UD aggregate. So UDAGG actually take the table as an input and generate one single scalar. In this case, if I aggregate a table just on column stock and get a sum for the stock number, the total would be adding all of them up, just to get one result. So Flink itself has some built-in AGG, the typical built-in AGG, but they are not sufficient because users always want to implement their business logic. So we have to provide the user-defined aggregate interface. To define the user-defined aggregate interface, we need to first understand how the aggregation works. So aggregation works in a certain way that you have a table input, and you keep applying those inputs row by row to the accumulator. So then we introduce a concept, accumulator, which saves the intermediate result. It's starting with the initial, create accumulator, initial state, and you applying the input one by one whenever the input comes. And then once it accumulated and saved to the accumulator. So basically it needs a create accumulator method and then a accumulator method, which apply the inputs to the accumulator. And when it's ready to emit a result, we need another method called getValue, right? So you have the previous aggregate result saving accumulator. Whenever either window finish or you want emit at a certain rate, then you have called getValue, you get a result. So to remember, I was mentioned that to ensure the exact ones and stabilities, we have to put this status accumulator into the backend state. So that's how the entire aggregate working in the streaming. So this is a simple interface. We have three methods: create, accumulate, get value, accumulate. The above two is defined in the interface. The third one is a contract method because the input is dynamic changing. You cannot put into the interface. Having this interface, user just need to override the method, implement the method, giving their business logic, and then use it in the SQL query. Okay, good. So this makes UDAGG working, but are we good? Is there any other challenges? Let's look at one problem. So assuming we counting the total visits on Taobao web page in real time. In our scale, we have millions, even 10 millions of the visits per second. If we dump through all those visits to one single node, boom, it won't work. Obviously, one single node cannot handle such amount of traffic, millions of the visits. So how we are going to solve this? We came up with an approach. It's traditional called local global aggregate. So on the first level, local aggregate, we partition the traffic in a certain way. And in each partition, we accumulate a certain amount of data. You get a certain amount of data into one accumulator. On the second level global aggregate, you just merge the accumulator. This will basically, its idea is similar as a reduce and a map, right? So you reduce their load to different workers, and then you merge them together instead of handle everything on just one single node. So this means we need a merge method. User just need to implement the merge to merge different accumulator together. Previously, we only have accumulator. They say different. So merge also very helpful in the session window. If you're familiar with the session window, so session window means a certain way. But beginning, maybe two windows is separated, but when something coming in the between, the two windows could be merged together. So merge is very helpful in the streaming in session window cases. So motivated by this, we introduce the merge method. But are we good? Is there any other challenges? Let's look at another complex problem. In this case, the input is infinite, the keyword with certain number, and the user want to understand the final result. User want to understand the frequency per each count. For example, I want to understand the frequency, how many, how much happened for the count 1, count 10, count 100. In this case, basic query is like two grouping aggregates. The first aggregate, you aggregate and key by the word, and you have the count number for each word. And the second aggregate, you basically aggregate on the count and see how many word has been appeared for one time. In this case, initial state is just one line. It's 1 and 3, means there are 3 words happens before, and their count is just 1, right? So let's say if we have a new word coming, hello 1, then the count for hello is jumping from 1 to 2, and then yes, we definitely insert a new value to the resulting table, 2 and 1, because there's only one word appear once. That's hello. So is this correct? No, because this value is incorrect. Because at this stage, only word and the bark has been appeared once. So the frequency for count 1 should be 2, not 3. Why this happen? Because when we adding 2 and 1, we forgot to retract 1 by 1, because it's basically, it's happened like when we're increasing something in the intermediate result, we have to tell the final result and revise final result and saying, hey, some word, previously it was 1, but it has been changed. You need to retract count on the 1. So that's the idea for the retraction. That's only happens in the streaming.